So let's continue. The next talk will be by Gabriela Jeronimo from the University of Buenos Aires, and she will speak on the effective differential Lüroth theorem.
Well, before starting with the talk, I would like to thank Alexei for inviting me here to participate in this webinar conference and give this talk. And well, what I'm going to tell you today is a joint work with Lizzie Alfonso and Pablo Serrano, both from the University of Buenos Aires, like me, on the effective differential Lüroth theorem. Well, I'll start by presenting the problem. This is such a long story from the beginning. In the algebraic case, the Lüroth theorem is the following statement. It says that if one has a field extension, K is a field, U is a variable, and we have an intermediate field L. Then this intermediate field is the field of rational functions in an element B of L. So this theorem was later extended to the differential setting by Ring and Colchin. And here it says that if now we have an ordinary differential field of characteristic 0, and U a differential indeterminate, whereas if we consider the smallest differential field containing S and U, and now G is an intermediate differential field between S and the field of differential rational fractions in U. Then there is an element in G such that this field G is the smallest field containing S and B. So this, again, these are now the rational fractions, but with differential polynomials in the numerator and the denominator. I will call such a B a Lüroth generator of the differential field extension. Some basic notation I will use. So throughout the talk, S will be an ordinary differential field of characteristic 0 with the derivation I will denote delta. C1, Cm are differential indeterminate that I will abbreviate with bold C. Or in general, when having a family of differential indeterminates, I will put the bold letter to represent all of them. So this will be the ring of differential polynomials in the variable C. That is the ring of polynomials in these variables, and all they are successive derivatives. Now the derivation delta is extended like this. Then the notation that I already used is the fraction field of this ring of differential polynomials, and with the derivation extended respective. And for a differential quotient of differential polynomials G, I will denote the order in the variable Ci. It will be the maximum of the orders with that the variable appears in G, and the order of G will be the maximum of the orders of all possible differential indeterminates appearing. So we are interested in computational aspects of the differential Lüroth theorem. It has also a story, but in order to analyze these aspects, we consider a subfield G, which is finitely generated. That is, we are given a finitely many differential fractions, P over Q. We assume that for each of them, the numerator and the denominator are relatively prime polynomials, and that their quotient is not an element of the base field. And the main goals of our work were first of all to give a priori upper bound for the order and degrees of differential polynomials giving a Lüroth generator of the extension. That is, we want to estimate the order of this B in terms maybe of n, the number of generators, the orders of the generators, and the degrees of the numerator and the denominator, both for the order and for the degrees of the polynomials appearing here. And the second goal was to have a finite procedure to compute a Lüroth generator of the differential field extension. Well, just to mention some previous work on the Lüroth, effective Lüroth problem. In the classical setting, it was addressed by Söderberger in 1986. I'm just mentioning the recent work on the subject, and then the procedure were refined in this and extended to the multivariate case in this more recent work. And in the differential setting, we have this work of Gao and Xu, which is an algorithmic version of Ritz proof of the differential Lüroth theorem. But here, no quantitative results were given. That is, they don't study the problem of estimating the order or the degrees of the numerators and the denominator of the Lüroth generator.
And was that algorithm for the ordinary case of any number of derivations?
Sorry?
What was the number of derivations?
Ordinary case, I think. If I remember well, it's ordinary case.
Well, we have the author here, right?
Maybe she knows better than me, but I think it was for ordinary.
Just using the differential characteristics set.
You see, the differential characteristics in the ordinary setting. Am I right? No? Both were ordinary differential fields.
No, how many derivations?
I don't know. There is no quantity. He said that. She said no quantitative result on complexity bound. It's just an algorithm. We can compute it, but no complexity analysis.
Yeah, but my question was how many derivations did you have?
In your field, in your right field.
Ordinary. Sorry. It's not true in the partial case. I think
No.
who gave a counter example. Even in two derivatives,
Yeah.
the Lüroth is not true in the partial case.
So, the first result we have is an upper bound for the order of any Lüroth generator of the differential field extension. It's stating that it will be of order bounded by the minimum of the order of the given generators of the field. So the proof of this is quite elementary. I'm not giving it here because of lack of time, but it's quite elementary. And the difficult task is to bound the degrees of the polynomials given the generator. Just a comment that all Lüroth generators have the same order because they differ by homographic map with coefficients in the base field, so they all have the same order. So it's a bound for any Lüroth generator.
How do you define the order of the quotient, sorry?
Sorry?
The order of the quotient? How do you
The maximum of the orders of the numerator or the denominator.
Oh, the maximum of both.
Of both. Yeah. So in order to come to a degree upper bound, we follow this approach and study the degrees of certain polynomials appearing in the computations. So this is the general setting. So we consider the prime differential ideal, which is the kernel of this map. That is, the x go to, we have new indeterminates x, each of them represents one of the generators, and the variable u remains unchanged. So the kernel of the map is a prime differential ideal, P, and n is a polynomial such that no coefficient lies in the ideal P when regarded as a polynomial in the variable u, and with the lowest possible rank in u among all polynomials with this property. Then we have that when we specialize the variables x in the given generator, we get a minimal polynomial of u over g. So this is a polynomial of minimal order and degree and rank, everything. Here is a minimal. So, and using this polynomial is that one can get a characterization of a Lüroth generator. So, there exists such a polynomial with lowest rank in u, satisfying this order bound, that is again the maximum of orders of all numerators or denominators in the given generators. This says in particular that this polynomial lies in the prime ideal we were considering intersected with this polynomial ring. Remember that this ideal P was a prime differential ideal in the ring of differential polynomials, that is infinitely many variables. Now, when this order bound, we know that the polynomial n in fact lies in this ring, this polynomial ring, infinitely many variables. In order to prove this, we use some estimates of order for characteristic sets, which were proved by Brahim Sadiq, and then a result of ours about the Hilbert-Bachin function of this ideal, this differential ideal P, which is involved here. And the characterization, in fact, is that a numerator and a denominator for a Lüroth generator can be obtained just by specializing this polynomial m. In this polynomial m, the variables x in suitable chosen elements of the base field. So it's just if we know the degree, the bound for the degree of this polynomial m, we will have a bound for the degree of the polynomials p and q appearing as numerators and denominators in the Lüroth generator. And we just need a bound for the degree in the variable u because the x will be specialized at the end. So the next task was to bound the degree of this polynomial m of lowest rank in u lying in this intersection.
Is that m like a Chow form or something like that?
I don't know. I don't know. So we consider these polynomials. Remember that the idea was that the variables xj were representing the p over qj, that is the generators of the differential extension. So from this generator we construct the polynomials xj from 1 to n, and we have a polynomial system S. And it turns out that the ideal P is the unique minimal prime differential ideal of this differential ideal generated by one event that does not contain the product of the denominators of the given generator. Moreover, the intersection of P with the polynomial ring in the derivatives up to order E. This is exactly the intersection of the polynomial ring, which is the saturated by Q of the ideal generated by S and all their derivatives up to order E. This intersected, of course, with the same polynomial ring. in order to prove this identity, we use we have to estimate the difference. We have to make some differential index analysis of the ideal P and S appearing here. And so now we are in a situation of a polynomial ring, of an ideal in a polynomial ring, in a bigger polynomial ring, intersected with this smaller polynomial ring. Here the variables involved are from x up to x2 times e, because the order of the input was e, and we differentiated e times. So now we have 2 times e.
And what is the differentiation index analysis? What is
But
this?
we have to determine how many times we have to differentiate these polynomials in order to get the ideal P, and it has to do with the differentiation index of the ideal.
So this equality is true for all e?
Sorry?
This equality is true for all e? Yes or no? What's the...
I don't understand your question, sorry.
So could you explain the second bullet? So what? So it's a statement, okay?
Yes.
Is it for all e?
No, it's for the E, which was the maximum order of the polynomials X. The polynomials S1 and N, which were constructed from the given generator, is the maximum of the orders appearing here was the number E.
Yeah.
For this numbering, it turns out that this identity holds because of the differentiation index of the system.
But this seems to be a standard result for constructing a dimension polynomial, correct? Because it's f is a non-reduced set, isn't it?
Yes, if I'm not to reduce set. So, yeah.
Yeah, so then the way, so if you just cut out the in the colon ideal, if you cut out a piece up to a certain order, you automatically get generated by the original reduced set and all its prolongations.
Yes, maybe it's just that what we did.
Yes,
In
it's-
other words, yes, maybe it's the same you're telling here. Yes,
So it's a standard result from differential algebra.
maybe. Yes. Yeah, that was just a part of the proof. I'm trying to make the different steps of the proof. Maybe I'm speaking in a different language as you, but it may be the same thing. So when we have this equality, so this enables the computation of the polynomial m just by Grabner basis, because now we have to look for a polynomial in this intersection of this ideal with the polynomial ring, just to compute a Grabner basis of the ideal using a lexicographic order when the variables x are smaller than the variables u, and take the smallest polynomial in the Grabner basis that contains some of the derivatives of the u. Then we specialize the variables x in a suitable manner, and in this way we obtain the Lüroth generator. So finally, to get the degree bound, we again consider the first e derivatives of the polynomials with the condition q different from 0, which is the, let's say, the geometric counterpart of the algebraic ideal appearing here. So we consider the affine variety, which is the Zariski closure of this set in this affine space. So the ideal is the vanishing ideal of this variety. And analyzing a suitable linear projection of the variety, we prove that the degree of the polynomial m we are looking for in the variables u is bounded by the degree of the variety b defined here. So now, in order to bound the degree of n, we have to bound the degree of b. We could do this just using the Bezout bound, which will be the product of the degrees of all the polynomials appearing here, but that gives an exponential bound in the number of variables. In order to avoid the exponential bound in n, which in fact is a bound greater than the actual bound, we make a more detailed analysis, which also involves Bezout's theorem, but also it's like an ad hoc analysis for these particular polynomials, which are derivatives of a given s. So what we get is that the degree of the variety is at most this number here, where the n does not appear in the exponent. It's just exponential in e, which was the order, but not on the number n of given generators. So using this, and the fact that the numerator and the denominator of the Lüroth generator were just specializations of them, we get this degree bound by with this exponential number. So summarizing, well, here are our results. So we have an ordinary differential field, U, which was differential transcendental over S. We have an intermediate field between S and the fractions in differential fractions in U, given by a finite number of generators, each of them given by relatively prime differential polynomials of order bounded by E and degrees bounded by D. So any Lüroth generator of extension can be written as a quotient of two relatively prime differential polynomials of order bounded by the minimum order of the given ones and degrees bounded by this number. And the Lüroth generator can be computed by Grendel basis applied to this algebraic idea where the polynomial sets are constructed like this from the given generators. Well, this is the main result. In fact, what we would like to get is a better algorithm to compute the Lüroth generator, because I know that Grendel basis computation could be really time-consuming sometimes, but this is like working to do yet. Well, thank you.
Any questions?
No question. Maybe we hope to see the formula on the previous slide for my question. So I guess I'm asking about the under the first bullet point, the degree bound that you get there. Do you know for a fact that it actually depends on n, in the sense that do you have examples which show that this is actually
no, all
tight?
examples are far from this.
Okay.
I think. Yes.
Yeah.
Yes, but yes.
Okay.
So because the number inside the bracket, what exactly is that number? Is the number inside the bracket, is it the...
Which number? This one?
The whole number inside the bracket?
Yes.
What is it? Is it the degree of something?
Let me remember.
So I'm just thinking if it's the degree of the variety defined by f.
This number, the degree of the variety defined by f, I really don't remember. I think it's not, but...
It's because in the previous one, you said that you can estimate the degree of the variety both v.
Yes.
There. Wait.
Yes.
You can estimate. So.
Yes, but this variety involves all.
That's
things.
right. And you say you can estimate the degree of that variety in terms of these other values. So does that mean that the degree of v is less than or equal?
The degree of v is less than or equal than this number here.
Right. And,
Yeah.
and so the thing inside the bracket, the d is the degree of the polynomials.
The d is the degree of the polynomial.
The n
N is
was,
the number of variables x.
right? And the e was the maximum of the orders of the
Yes.
the e.
Yes, e plus 1.
Uh-huh.
E was the maximum order, yes.
Okay. Okay. That. Thanks.
Okay.
More questions?
For this construction of this, the idea where you get all the construction, you were talking about the unique prime ideal P inside, this curly P.
Okay.
Here.
I see here.
Yeah.
Yes.
Do you have a feeling of if the dimension of this P influences the kind of result you can give, or like the characteristic set of this P is given by one?
Yeah,
or
the
more
characteristic
polynomials?
the characteristic set of this ideal will give you the polynomial M you're looking for.
Mhm.
Yes. But then what we tried to do was to turn the situation to an algebraic polynomial ideal, not to compute the characteristic set. But I think that looking for a characteristic set of P was the idea behind reciprocity.
Right, but anything to do with the dimension of the ideals you get, you then reduce the problem to an algebraic ideal.
Yes.
And you fill it up.
But yeah, and we forgot about P when
Yes, I know, but
I think that the dimension must appear in the
no,
numbers.
doesn't play a role in the result.
I don't know, but I'm not sure.
Do you propose to do a prime decomposition of the polynomial ideal?
Yeah, I don't know. I was wondering if this could, if they look at that, if this could have an influence.
Do you propose to do factorization for that? Maybe they want to avoid that.
Yeah. Yes, maybe factorization might be possible.
Any other questions?
Okay, I have another question. So are you interested in doing this, just as a general question, for sort of arbitrary differential fields, or would it be satisfying enough to do it, in the case that the F there was, say, differentially closed or something like that? Or I mean, are you interested in having more assumptions ever on the field F that you work over, on the differential field? Like would it be a big barrier to assume that F was differentially closed?
I don't know if it
Why do you
would
ask
make
this
any
question?
difference.
Oh, I think you could get rid of the N in that case.
You think, so
Yeah.
you might need to be differential close to get real?
No, I don't think you need to, but I think I see how to do it.
Okay.
I don't know.
But I don't know how to do anything
The
with
thing,
non-differentially
the thing is
closed
that you
fields.
believe that the n shouldn't be needed, right? That's the point.
Yeah, or maybe just different. I don't know if I'd say that's wrong.
More questions, comments? Well, thank you. This is certainly very interesting. There are many more things to prove in bounds in differential algebra. So thank you very much for bringing this up.
Thank you.
The formula is the same except for the n, right?
Well, yeah, but that's just because it's a Bazooka form. They all look the same. I mean, it's not. This is just.
Yeah, but,
You're talking about the sort of formula that
yeah, but the n doesn't have a